Okay, so welcome to today's Congruences seminar. Today our speaker is Daniel Vargas Montoya, and he'll speak about congruences, modulo P, algebraic independence, and monodromy. Please.
Okay, so thank you very much for this invitation. So my talk is about congruences, modulo P, algebraic independence, and monodromy. So the main goal of this talk is to see the link between these two third terms, congruences modulo P, where P is a prime number. Actually, congruences modulo P means algebraicity modulo P, which I am going to define in a few minutes. Algebraic independence, during the talk, algebraic independence deals mainly with the algebraic independence of G functions, or more precisely with diagonals and hypergeometric series. And finally, we have the classical notion of monodromy. Okay, so let me start with the definition of algebraicity modulo P. And so we have the ring ZP is the ring of rational number AB, so that AB are coprime and P and B are also coprimes. So we can reduce the element of ZP modulo P, and the residual field is SP. Okay. So if we take a power series with coefficient in ZP, we can consider its reduction modulo P, and the reduction is actually the reduction of each coefficient of F modulo P. So that like this, we obtain a power series with elements in FP. So here is the definition. We take a power series with coefficient in Q. So we say that F is algebraic modulo P if, first of all, we can reduce it modulo P, and the reduction is algebraic over SPZ. Okay? So given a set S of prime numbers, AS is the set of power series, so that for all P in S, F is algebraic modulo P. It means we can reduce it F for all P in S, and the reduction is algebraic over SPZ. So now, if F is algebraic modulo P, so we are going to denote dig F modulo P, the degree of the minimal polynomial of F modulo P. In other words, is the algebraicity degree of F modulo P. So here is the main example of algebraicity modulo P, is the main example in this talk. And this example is about Peluca's congruences. So we say that a power series F is Peluca if the constant term is 1, and if we can reduce F modulo P. And the third condition is the most important condition. This condition says the following thing. For all integers m and for all r between 0 and p minus 1, we have this equality, modulo P. Okay? So actually this third condition is equivalent to the following statement. So we take F a power series with coefficient in ZP, and also the constant term equals 1. So F is Peluca if and only if the reduction of F modulo P is equals to AP times F modulo P to power P, where EP is the truncation of F modulo P. Okay, so from this relation, of course, we see that if F is Peluca, then F is algebraic modulo P. So usually we are going to use this relation instead of this condition. Okay, and of course, as I said, if F is Peluca, then F is algebraic modulo P. The main point here is actually the most of the power series that are Pelucas for infinitely many prime numbers P are G functions. Okay, I am not going to recall the definition of G functions. However, I am going to give the definition of the two important classes of G functions, which are hypergeometric series and diagonals, because usually the G functions which are Pelucas are diagonals or hypergeometric series. Okay, so here is the definition of the hypergeometric series. Maybe you know this definition, but I'm going to recall. So we take two vectors alpha and beta with coefficients in Q, which are not negative integers. So the hypergeometric series associated to alpha and beta is given by this expression, okay, where this symbol is the Pochamer symbol. This symbol is defined as follows: for a real number x, x0 is 1, and g is the product from I0 to g minus 1 of x plus I, for g bigger than 0. Okay, so that is a power series with coefficients in Q, and the constant term is 1. So here is an example of the hypergeometric series, which is Peluca for an infinite set of prime numbers. So we take alpha as 1 over 5 and 1 over 5, and beta 2 over 7. So it turns out that for all p congruents to 1 modulo 35, this power series is Peluca. Okay? It's okay. And here is the definition of the diagonal. So we have the diagonalization operator. It's defined from the power series in the variables, which are also rational functions. And it just takes the diagonals coefficient of the power series. So it's a basic definition. So we have the image of delta D, and D is the all onion of dd. So we say that f is a diagonal of a rational function if f belongs to D. Here is some examples. For every r bigger than 0, we define this power series, which is also a hypergeometric series, this series Fr. So this series Fr is a diagonal, and by using the Lucas theorem, actually we can show that Fr is Peluca for all p. It's important to mention that this hypergeometric series is not a diagonal, okay? So here is another example. This example is given by the generating power series of a Paris numbers. This series is also a diagonal. This power series is not a hypergeometric series, okay? So by using a result due to Gesell, the power series T is Peluca for all P, okay? So before talking about the algebraic independence, I would like to show how the Pelucan's congruences appeared into the picture of the transcendental results. Okay, so according to my understanding, that the point star is this conjecture due to Stanley. The conjecture says that the power series Fr is transcendental over QC for all integers r bigger than 1. I recall you that Fr is this power series. We exclude r equals 1 because F1 is algebraic. Okay. So this conjecture was proven by Sharif Woodcock. Here it's important to mention that we can also use the result of Buchers-Hegman to prove this conjecture. But in this case, we are going to focus in the approach given by Sharif Woodcock. Okay, so how they prove that? First of all, they show that the sequence, the algebraicity degree of Fr modulo P is not bounded, because in general, a general statement is if F is algebraic, F is a power series with integer coefficient and algebraic, then this sequence is bounded. Okay, so for this reason, they prove that. Now, to do this, they use the fact the Fr is Peluca for all P. Of course, in the argument, it's also important that R is bigger than 1, but the main point in the proof is that Fr is Peluca for all P. After that, we also have Alous, Guyot, Bouchan, and Skordev show that if F is Peluca for almost prime number P, then F is algebraic if and only if there exists a polynomial P, the degree less than or equal to 2, so that the constant term of P is 1 and F is the root square of 1 over P. Okay, so by using this result of Alous-Guyot-Boucham, we can also show the conjecture of Stanley. And because FR, the minimal operator of FR has order 2. So, or I'm sorry, order R. So, but we can also use this result to get to show that some G functions are transcendental, as for example the series T. The series T is transcendental over Q, and again the main point here is the order of the minimal operator of T is 2. So now we have that FR and the T are transcendental. So the question is, are there algebraic relation between FR and T? So we are going to see that actually to study or to get this kind of algebraic relation is again very important, the fact that FR and T are Pelucas. So here is a general definition to generalize the Pelucas congruences, let's say. So we take S a set of prime numbers. So the set LS is the set of power series with coefficients in Q, so that for all P in S, of course, we can reduce F modulo P. There exists a positive integer L bigger than 0 and a rational function AP, so that we have this equality. But there is a third condition. This condition is about the height of AP. The height of AP is less than or equal to C times 2P to L, where C is a constant independent of P. I recall you that the height of AP, since AP is a power series, so AP is equals to R over S. So the height is the maximum degree of R and S. Okay. So the main observation here is that if F is Peluca for all P in S, then F belongs to LS. Why? Because let me come back to the definition of Peluca. Because we have this relation. So here we can take, since AP is this polynomial, so we can take C equals 1 and L equals 1. So in this case, it's immediately that if F is Peluca, then F belongs to LS. And also it's important to say that for the moment, the only example that we know in this set LS is the Pelucas. But it's according to the definition, more general. So here is the theorem due to Adamczewski, Bell, and the leg. So we take a power series F1, FR in LS as a finite set of prime numbers. Then the power series F1, FR are algebraically dependent over QZ if only if there exist integers MI, MR, not all 0, so that this product is a rational function. Okay, so maybe as you know, this theorem is very close to, at least the conclusion of this theorem is very close to the Colchin theorem. So let me recall the Colchin theorem. So we have a power series F1, FR. So we suppose that for all I, Fi is a solution of a differential operator of order 1 with coefficients in Q. Then F1, FR are algebraically dependent over QC if only if there exist integers M1, MR, not all 0, so that this product is a rational function. So the conclusion is the same, but the hypotheses, of course, are not the same, because in the Colchin theorem, we need that Fi is a solution of a differential operator of order 1, and that is not the case for a power series. It's not necessarily the case for a power series in LS. As for example, we already know that FR belongs to LS, but the minimal polynomial, but the order of the minimal operator of FR is R. Okay, so now by using this theorem of Adamczewski, Bell, and the leg, we can show that the power series F2 and T are algebraically independent over QC, and for example, we can also show that FR for R bigger than 1 are algebraically independent over QC. So with the aim of applying theorem 1, a natural question is when a power series belongs to the set LS. So that is the main question we are going to answer in this talk. So here is the strategy we are going to develop during the talk. So I recall you that AS is the set of power series, so that F is algebraic modulo P for all P in S. So by definition of LDS, LS is inside of AS. So if we want to know when a power series belongs to LS, so the first step is to give a criterion to determine when a power series belongs to AS. Okay, so this criteria is based on the notion of a strong Frobenius structure for P. Generally, this criteria, generally we have that a strong Frobenius structure for P implies algebraicity modulo P. More precisely, if we take a power series F with coefficient EZP, which is a solution of a differential operator having a strong Frobenius structure for P, then there are rational functions A0, AK not all zero, so that we have this equality. Okay, we are going to see that more precisely in a few minutes, but we are going to use the maximal unipotent monodromy in fact to get something like this. So a strong Frobenius structure gives this kind of equation, and by using monodromy, maximal unipotent monodromy, we are able to pass from this kind of relation and to relation like this. Okay, so here is the definition of a strong Frobenius structure. So we take QP bar be an algebraic closure of QP, and CP the completion of QP bar with respect to the periodic norm. And the field CPZ is equipped with the Gauss norm. The Gauss norm is defined like this: is just the maximum of the norm of AIs over the maximum of the norms of BG. So the field of analytic elements denoted EP is the completion of CPZ with respect to the Gauss norm. Okay, so here is some remarks for all prime numbers P. QC is inside EP because QC is inside of CPC. Okay, that is clear. The field EP is equipped with the usual derivations, and the residual field of EP is SP bar Z. Now, here is the definition. This definition is due to York. So we take a differential operator L in EP of order N. We say that L has a strong Frobenius structure of period M if there is a non-null and not zero vector, and so that for all solution F of L in a differential extension of EP, this expression is again a solution of L. So the main point to keep in mind is that actually the Frobenius structure is a Frobenius action over the solution of L. That is the main point. Now, if we take a differential operator L with coefficients in QC and P a prime number, we say that L has a strong Frobenius structure for P of period M if L viewed as an element of EP has a strong Frobenius structure of period M. I recall you that QC is inside EP for all P, so we can see L actually as an element of EP. So here is the theorem that shows that a strong Frobenius structure implies algebraicity modulo P. So we take a power series F with coefficients in ZP, solution of a differential operator L with coefficients in EP. So if L has a strong Frobenius structure of period H, then the power series F modulo P is algebraic over FPZ, and the algebraicity degree is bounded by P to N squared times H, okay? Where N is the order of L. This is important. So more precisely, the proof of this theorem show that there are rational functions, not all zero, so that we have this expression. So it's clear that from this expression, we get that f modulo p is algebraic, because the rational function, not all these rational functions are not zero. And also we get that the algebraicity degree is bounded by p to n squared times h. But we are looking for relation of this shape. Okay, so as I tell you before, the main idea is to use here, we are going to use the condition of the maximal unipotent monodromy. Actually implies we can, from this condition, we can use the maximal unipotent monodromy to get a relation of this shape. Okay, so now I'm going to give some example of the differential operator having a strong Frobenius structure for almost prime number p. So these examples are mainly the hypergeometry operators and Picard-Fuchs. So we take again two vectors alpha and beta with coefficients in Q which are not non-negative integers, and we set d alpha beta the least common multiple of the denominators of alpha e and beta e. Okay, so the hypergeometry operator associated to alpha and beta is given by this expression, is the definition. So here is the theorem. If alpha e minus beta g is not an integer for all I and g, then for all prime numbers p bigger than d alpha beta, then the hypergeometry operator associated to alpha and beta has a strong Frobenius structure of period phi d alpha beta, where phi is the Euler's totem function. Okay. Now the second example is given by Picard-Fuchs equation, and these examples, the proof is let's say the fact that the Picard-Fuchs equation has a strong Frobenius structure for almost p comes from algebraic geometry. Okay. But these two examples are very important, because actually by using these two examples, we can use the theorem 2 for hypergeometric series and diagonals. Why? Because the theorem 2 says that if we can reduce f modulo p, and f is solution of a differential operator having a strong Frobenius structure, then the reduction is algebraic, and also gives a bounded of the algebraicity degree. So the hypergeometry series actually are solution of the hypergeometry operator, and the theorem 3 says that the hypergeometry operator has a strong Frobenius structure. Now, if we take a diagonal, it's a result due to Gilchrist that a diagonal is a solution of a Picard-Fuchs equation, and we know that the Picard-Fuchs equation has a strong Frobenius structure for almost all p. So for this reason, we can apply theorem 2 for hypergeometry series and diagonals. Okay, of course, we have to be careful, because we need the condition that we need that f can be reduced modulo p. Okay. So let me recall the notion of maximal unipotent monodromy at 0. So here we take k in a field. So we say that this differential operator with coefficient in key C is mom at 0 if for every I, actually bi is also a power series. That means 0 is not at pole, is not a pole of bi, and the evaluation of bi at 0 is 0 for all I. Okay, so this is the algebraic definition, but of course, if you take k as the field of complex numbers, this definition is equivalent to the geometry definition. Okay, so now we are going to take a differential operator D with coefficients in QC, and we are going to consider dp the reduction of D modulo P. Okay, now that we can reduce D modulo P for for almost prime number P, because this is an operator with coefficient in QC. Okay. So we consider the following two sets. Ker D is the set of power series, so that F is solution of D, and also we consider this set. This set is the Lorentz series with coefficient in P, so that F is solution of dP. Okay, so it is well known that if D is mom at 0, then the dimension of this set as Q vector space is 1. So that is the main motivation to consider this condition, because we know that the dimension of this vector space as Q space vector as over Q is 1. So there is the question, maybe it happened the same thing in modulo P, and the answer is yes. So that is given by this proposition. So we take a differential operator dP with coefficient in Fp bar C, mom at 0. Then there exists a polynomial P, which is not 0, so that P is solution of dP. And actually, the dimension of this set as Fp bar C to P vector space is 1. Okay, so that is actually the main motivation to consider this condition. And actually, this condition implies this kind of equality. Okay. So here is the main result. So we take S a set of prime numbers. So the set MFS is the set of power series with coefficients in Q, so that we can reduce F modulo P for every P in S. F is a solution of a differential operator H having a strong Frobenius structure for every P in S. And the third condition is that F is a solution of a mom differential operator D. Of course, M comes from monodromy and F comes from Frobenius. So here we have these three conditions. Let me say that this set is very rich. There is many elements inside. It's not an empty set. So we had this theorem. We suppose that S is a finite set of prime numbers. So we take F inside MFS. Then there exists a S prime inside S and a constant C bigger than 0, so that S minus S prime is finite, and for every P in S prime, we have this equality. Okay, it means that F modulo P is equal to AP times F modulo P power P to L, where AP is a rational, of course, is a rational function, and the height of AP is bounded by C times P to L. Okay, so I recall you that the main motivation was to know when a series belongs to LS, but I recall you that to a necessary condition to belong to LS is this condition: the height of AP is bounded by C times P to L, and in the main result there appears a factor 2 in the power. So that is a kind of problem because it's not in LS. So and let me say that the main point to know when an element is in the LS is with the aim of applying theorem, the criterion given by Adamczewski, Bell, and Delec. So the first try is maybe to know if the proof given by Adamczewski, Bell, and Delec works when there is a factor 2 here, but the proof doesn't work. We need really withdraw the 2. So there are two options. Maybe we can do better and to show that an element of the MFDS, the height, is bounded by C times P to L, or maybe this bounded is the best possible. It means we can do better than that. So actually, the result is that this bounded is the minimal, is the optimal. Why? Because there are power series in MFS which are not element in LS for any unfinite set S of prime numbers. So for that, let me introduce the power series GR. It's given by this expression. Actually, GR is a hypergeometric series. So here is the theorem. Let S be an unfinite set of prime numbers. Then G2 doesn't belong to LS. However, for every R bigger than 1, GR belongs to MFP minus 2, where P is the set of prime numbers. Okay? Why? Because actually GR is solution of this hypergeometry operator. So thanks to the theorem 3, this hypergeometry operator has a strong frobenius structure for all P bigger than 2, and it turns out that this hypergeometry operator is also mum at 0. So we can apply this theorem, the theorem 4, and we have this equality, and also we have that, but we can do better than that for this hypergeometric series because it's not in LS. Okay, so in this point there are two things. On the one hand, we want to know when an element of an element of this set is in LS, and also another question is we want to study the algebraic independence of the elements of this set, because as we have seen, we cannot apply the criterion given by Adamczewski-Deleg, because there are elements in this set which are not in LS. Okay, so we are going to, in the last part of the talk, I'm going to answer these two questions. So we have a more generalized Pelucas. So in this result, I'm going to show when an element of MFS is in LS. Okay, so for that, let me recall the Cartier operator. It just we have a power series, and we also take the coefficients which are divisible by P. So let S be an unfinite set of prime numbers. Suppose that F is an element of MFS. If for every P in S there is an integer LP bigger than 0, so that we have this equality, then F belongs to S prime, where S prime is inside S, and S minus S prime is finite. Okay, maybe at the first sight this theorem appears technical, but for example, actually to show this equality, we use the Lucas theorem, and more precisely, for example, we can use this theorem to show that, for example, the series FR I defined at the beginning and at the series T belongs to LP minus G, where G is a finite set of prime numbers. And in a more significant way, among the 400 power series in the paper tables of Calabi-Yau equations, we can use this theorem, for example, to show that 242 of them belong to LP minus G. Okay, so yeah, at the end it's not very technical, but for example, in these two cases, to show this equality, we use the Lucas theorem. Okay, and finally, here is a result of algebraic independence. So of the elements in MFS. So we take a power series F1, Fr in this set, S unfinite. And we need some auxiliary power series. So in this theorem called GI, which are power series in Q, so that for all P in S, we can reduce the power series GI. Okay. We suppose that for all P in S and all I between 1 and R, there are an integer bigger than 0, so that we have this equality. Okay, again, this equality seems a little technical, but the most important thing of this theorem is the following one. If the auxiliary power series are algebraic independent over QC, then the power series F1, Fr are algebraically independent over QC. The main point of this theorem actually is the following one. Under the assumption of this theorem, we can show that actually the power series GR belongs to LS prime, where S prime is inside S and S minus S prime is finite. So somehow this theorem gives you an algebraic independence transfer theorem from LS to MFS. Okay, and again, for example, to show this kind of equality, we use the Lucas theorem. But this theorem is helps to study the algebraic independence of some elements in MFS, which are not in LS, but it's not so general because in many cases we don't know if this auxiliary power series exists. Okay. However, we can apply this theorem to some power series, as for example, the power series GR for R bigger than 1 are algebraically independent over QC. Here is very important to say that if for example, for this family, we cannot apply the theorem given by the criterion given by Adamczewski, Bell, and Delec, and it's the same thing for these two power series. The power series G2 and the power series T are algebraically independent over QC. So to finish, let me show how I prove the first one. I recall you that we have GR, by definition, GR is this power series, okay? And also we have FR. So then by using Lucas theorem, we have this equality. That is the main point in the last theorem. But we know that GR actually belongs to MFP minus 2. And according to corollary 1, we know that this power series FR are algebraically independent over QC. So by using the last theorem, I think it is theorem 7, we can conclude that the power series GR are algebraically independent over QC. So that is all. Thank you.
All right, thank you so much, Daniel, for this very nice talk. Do we have any questions or comments? Please, you can just unmute yourself. You can also ask in the chat if you prefer.
I have some questions, if I may.
Sure.
Thanks. First, thank you for the really nice talk. I look forward to studying this in more detail. I had a few naive questions. So this set MFS of power series satisfy like certain kinds of operators. If I remember, you want them to evaluate to 0 at 0, but there's some other conditions.
Yeah, then may come back. Here is
right. So I'm so it's not obvious to me whether this a priori just a set of power series, if it has any kind of reasonable closure properties. Right now, since you want the leading term to be exactly 1, maybe not, but somehow if you multiply 2 of them, do you get another one?
yes, or maybe for example as the derivation. Actually, we can define a more general set. I call it L2S because of these two. So actually MFS is inside of this of L2S. And L2S, for example, is closed on the derivation, for example. And I for example, another question is closed on the Hadamard plot. I don't know. Because that is one of the nice thing of the Pelukkas congruences. Pelukkas congruences are closest under Hadamard product. But if you take a generalized Pelukkas, it's not. And I think it's the same thing for this set MFS. But okay, you can add, but if the first constant, if the constant term is not 0, you can divide. That is okay.
Right.
Yes. But at least there is the 2 and 3rd condition is I'm not very sure is if they hold. So
Gotcha. Thank you. And just a quick other one. You had mentioned that this a series that you pay special attention to the F sub R. If I remember right at the very beginning, you said that there were diagonals of some higher dimensional rational functions, but
yes.
Is it easy to say diagonals of what?
Yes, in this for this for FR, yes, and even for T. Actually, here you can take for FR is the product of 1 over 1 minus C1 minus C2 times 1 blah blah blah. And for T is more complicated, but it's in the
okay. And I'll try to sneak one last question, but it might be unreasonable. So please feel free to tell me that you don't want to. How much of this do you think you might be able to extend to power series that have only algebraic coefficients? You know, P could be replaced with a prime ideal in a ring of integers, and so on and so forth.
For you mean for when the coefficients are in Q bar?
Sure. Maybe only a very reasonable small number of you would start. Yeah.
I think is doable. Yes, because the techniques are almost the same, but it's doable because you can define, of course, Frobenius structure for when the operator is in Q bar. That is okay, and also the notion of monodromy. So I think it's the same. Yes.
Thank you.
Welcome.
Okay, any other questions or comments? Okay, so if not, let's thank Daniel again.
Thank you.
And then let me also remind you that there is no corking seminar next week because there is the Dart in Kassel, but the corking seminar will return in 2 weeks then.